after depressurizing and draining, you open the end closure of the receiver barrel, and then you can pull your pig out. Along with that, all the dirt and sludge and mud is going to also come out, and the whatever slurries and the kind of a carbon steel pipe rust can also come out, which is also called scalp, that also can come out. So you can just remove all that, clean the receiver barrel, make it free of hydrocarbon, purge it with nitrogen, close the enclosure, and keep it preserved with nitrogen to avoid the any corrosion reaction to take place. So this is the typical pipeline system, and to be able to perform all such activities, okay, we need all these elements to be designed and installed in the pipeline. Design means, like we have seen the pipe for the pipe thickness calculation based on the hoop stress and the longitudinal stress. So all these elements should be capable of withstanding the internal pressure involved in that pipeline. So which normally we consider as a design pressure, because we with all the possible required margins, factor of safeties and all that, the design pressure and all these elements should be designed for that design pressure. We are going to see the design of every element and its material selection and its procurement specification, how to specify them for the procurement, typical data sheets and all in the future series of this future lectures of this series. But today we are going to see basically all the elements. Okay, so now let's move to the individual elements what are shown here, just to give you the brief background about it. Okay, so let's see the individual element. So in next few slides we'll cover that. So let's see first the pig trap. What is a pig trap? We'll do quick wrap up of all these elements, just for for everyone to understand what is that. So pig trap is an ancillary item of pipeline equipment with associated pipework and valves for introducing the pig to a pipeline or removing the pig from a pipeline, which I have explained you in the based on the overall system scheme, which I believe you would have understood now. This is how the pig is going to look like. This is the pig inserted in the pipe, and how it is going to look when it is going to travel. This is a cross section taken just for clarity. So this is a pig having multiple discs and brushes and wires and all that, which is going to run along the pipeline with the same fluid flow which is the pipeline is transporting, and along that it will remove all the deposits and it will push the stagnant liquid away, as I explained. So this pig will be inserted like this. This is the open one cross section of the typical pig trap, with the end door open, and how the inserted pig will look like. And then the other end of the pig trap is having a flange joint to which the mainline isolation valve will be connected. So normally you will also find that the major barrel and minor barrel, there are two barrels involved in the pig trap. The major barrel is always higher size so that the pig can be inserted comfortably, and minor barrel is normally exactly same diameter of pipe and same ID of the pipeline, so that the pig gets kind of a properly. Pig has got discs and cups, because it has to get properly interference fit in the pipeline, such that the upstream and downstream pressure difference should be able to exerted across the pig, and because of that only the pig is going to travel. Okay, so the cups or some kind of a discs are there which create some kind of a soft but interference fit, like gasket. When you are trying to insert the piston in the cylinder, this will be like acting like a piston, which will and behind the pig there will be higher pressure, and the downstream of the pig on the other end of the pipeline, sometimes you can even depressurize. You can open the vent, or you can reduce the pressure, and then because of the differential pressure you basically try to move the pig. So this is typical pig trap. This is another sketch of a pig trap in which the associated piping is also shown connected. So the first sketch shows you cross section, the second sketch shows you all the connections of the pick trap with the piping and all that, and you can see the kicker line also. So with the kicker line, the flow will be diverted from the bypass line to the barrel, so that the pick can be pushed through the barrel to the main pipeline. And similarly, the receiver. So this is a typical pick trap, the one of the most critical element of the pipeline. Then we will go to the next element, which is mainline or pipeline valve, which we just saw. So this is how it's going to look like, a typical valve with hand wheel, and depending upon the size and pressure rating, if the manual for the person to open or close with the hand wheel becomes sometimes very difficult, or it might take long time. In that case, it can be even automated. So it can be motorized, it can be having hydraulic panel, so that just by pushing the button, automatically the valve will open or close. Typically, we use full bore ball valve for mainline pipeline application, mainline valve applications, because we need a full bore matching with the through the valve, matching with the pipe ID, through which the pick should be able to pass. We cannot have a reduced bore valve in which the pick can get stuck. So we want through and through opening in the pipeline across the valve, and therefore all the elements involved in the pipeline, which is in the main flow path or pigging path, should have the proper ID control. The ID should match with the pipeline, pipe ID, so that pig can through and through travel through that, and should be able to maneuver we should be able to maneuver the pig across all such elements. So it is one of the critical aspect of the designing the pipeline elements. Pipeline valve is normally used for interrupting the flow, basically as simple as that. So pipeline valves are installed at various locations. We have seen in the system. The bypass valve is also pipeline valve. Pick trap isolation valve is also called pipeline valve. Kicker valve is also part of the pipeline valve, pipeline system valve. So it's basically going to interrupt the flow. Okay, it can isolate one section of the pipeline from the adjacent section. Okay, and it can isolate pick trap system from the pipeline, so that pick trap door can be opened safely, and we can insert the pig or retrieve or remove the pig from the door. So it can also isolate the pipeline from the pick trap from the main pipeline. The pipeline valve is normally either fully open or fully closed, except the bypass valve and kicker valve sometimes can be partly opened and closed. But it is not. They are not the mainline valve. They are not going to negotiate the peak. But wherever the peak passage is involved, the mainline valve, the valve will be either fully open or fully closed. Okay, the pipeline valve. Sometimes what happens? The pipeline is very long, and in case there is, assume that it is 300-kilometer long pipeline, and if there is a leak happening in the last 50 kilometers, like from 250 to 300 kilometer section, if there is a leak, okay, you don't want to waste the entire inventory in the pipeline to be leaking out. So if you can imagine that if you have some isolation valves installed along the pipeline length, let's say at every 30 kilometer or 50 kilometer, okay, then what happens is, where if the leak is happening in the last 50 kilometer section, then you can isolate the earlier valve, block valve, which is also called the sectionalizing valve or block valve. So by closing such valves, you can prevent the all the entire inventory in the pipeline to be leaking, and it will be basically helping you to in two ways. One is the environmental impact can be controlled, can be minimized, and your inventory, which is it's a money finally. Yeah, it is having a price. Yeah, so all this inventory can be saved instead of wasting to the soil or ground or atmosphere. So such valves which are installed along the pipeline for sectionalizing are also called block valves, and we design the block valve stations around them with certain features which we'll see in the future series. So what we have seen is the different types of valves we have seen in the system. So valve installed in the main pipeline flow path will have to be full bore and requires some special features to be able to negotiate the pig passing through the pipeline, as I explained earlier. And this, because of this feature, these valves are named as mainline valves or pipeline valves. You can always find this title used for such valves: mainline valve or mainline operating valve, MOVs. Typically in the oil and gas pipeline industry. So there are some other important isolation valves, which are bypass valve, kicker valve, and sometimes in the main pipeline like block valve stations and all that. So these are also important isolation valves, not necessarily always in the main line, but still they are important for the pipeline operation aspects. Now we'll move to the next part, which is going to be bar T. So we have seen in the mainline system that the bar T was shown, where the bypass pipe was connected to the main pipeline. So bar T is used in a pipeline system at any branch in the pipeline to ensure safe passage of the pig. So pig has to pass through the pipeline. So it has to be maneuvered along the pipeline. It cannot get disturbed, or it should not get blocked or stopped in between at the branch. So just imagine if you have a normal T installed where your branch is connected. What can happen is the pig can slightly get tilted when the opening is found, and then pig can get stuck there, and then it becomes a very difficult scenario to track such pig and then how to remove it. Because the pipeline is operational, it's a live pipeline. There are no openings available in the pipeline to fish the pig out. So it's going to be very difficult to avoid pig getting stuck at such branch locations where there are openings for the branch flow to either come in or go out, to be taken out. What we do is we provide such bars, bar Ts. So bars are welded exactly at the ID of the pipeline in such a way that the pig, if it tries to get slightly tilted, and it cannot stuck, it can, because the bars will not allow the pig to change its position while it is moving across the T. So you can easily see now the bar T, the importance of it. So whenever the branch sizes are more than 50% or higher, or above 50% of the opening, then normally the chances of pig getting tilted and stuck are very high, and normally bar Ts are involved. For suppose it is a 30-inch pipeline and you are providing 2-inch or 4-inch branches for the some very small drain lines or vent lines or pressure gauge connections, then you don't need bar Ts. But bar Ts are normally provided for more than 50% opening, where the pig possibility of pig getting stuck are very high. So this is, we have already seen the pipeline pig which is moving through the pipeline. Now we'll see a typical sketch where you can see this barrel and the bypass piping and the bar T, where the bypass piping connects to the main line. At that branch there is a bar T. Now you can imagine that if pig has to move across, how bar T is going to help. So pig is now reached just before the T junction, and because of the bars, pig cannot get tilted. It will just go straight in the pipeline, and we ensure that it will not get stuck. So this is the most important element in the pipeline system, the bar T. Okay, let's move to the next element. So this is what I said. The pig is about to pass through the bar T. So this is the location which is indicated with the cloud here. Now let's see the next element, which is pipeline flange. So pipeline flanges are basically required to connect the flange elements together. So it connects the pipeline with the components in the pipeline system by use of bolted connections. Why we need bolted connections, why we should not have all the welded connections, is for the simple reason that if you want to repair certain parts or maintain certain parts by removing them and replacing them, then welding will require cutting and the weld preparation, and you will need some extra space to be taken care, because you are going to cut out certain parts. So to make the maintenance and replacement easy, all such parts which require maintenance are normally bolted, with the flange connection. So flanges are very important parts of the pipeline, and they are used very commonly in the oil and gas industry. The most commonly used type of flange in the oil and gas industry is well neck flange, which is basically having a hub, and which provides some kind of a strength to the pipeline, and it provides smooth internal passage. It will not provide any kind of a crevice or any gap between the pipe and the flange. So it gets welded to the hub end of the pipeline, and the other end gets bolted. So weld neck is the type of flange normally used in oil and gas industry, whereas in the other type of piping industry, sometimes other types like slip-on, threaded, other type of flange connections are also used. But in oil and gas industry, weld neck is the most commonly used type of flange. The Sometimes the flange face is normally race face for the normal pressure ratings, say up to 1500 or 2500 pound class ASME B 16.5 ratings. Uh, Whoever are having experience in this design field will understand what is flange rating. For the beginners, we will cover it later. But up to 2500 pound class ASME B 16.5 flange ratings, race face flanges with the spiral wound gaskets is the typical application used. Whereas for API 6A design, which is 5000 psi and 10,000 psi, 15,000 psi kind of a very high pressure ratings, normally we go for ring type gasket joints, which is having a groove and a ring. So this is used for the very high pressure applications. Normally in the wellheads, the pressure is very high. It is connected with the reservoir pressure, where these API 6A flanges are used with ring type and groove type joints. We'll see quickly some pictures about how these flanges look like. Flanges are also important because uh, the flange rating is always gives a representation of the what is the pressure of this in this pipeline in the pipeline. So the most commonly used international standard for the flange rating is ASME B 16.5, and this standard plays very important role in assigning the pressure rating to the piping or pipeline systems, which we'll cover later during the detailed design of the design pressure aspects and the flange aspects. But uh, so the flanges and flange ratings are the most critical elements in the pipeline system. We'll see some pictures how weld neck flange looks like. So this is how the weld neck flange is welded to the pipe, and it provides a smooth internal passage. For the as we know, the pigging also, and from the corrosion point of view also, no crevice is formed. It is very smooth um, pipe to flange connection, and the weld neck flange hub is shown where the pipe is welded. This is how the one example is given where the flanges are welded to the pipe, and then in between such two flanges, the valve is connected. So basically, this is a flange valve which can be removed and inserted or replaced, whenever required. So that is the advantage of having a flange joint. And this is a typical ring type joint shown, which is for high pressure. So you can see a groove in which a loose ring is inserted, and then it is basically used for the very high pressure applications. Let's move to the next topic, which is pipeline isolation joint, the other element. This is also very important element where the pipeline is buried. Okay, so where the above ground to buried transition takes place. Okay, the isolation joint or monolithic isolation joint is provided. What this joint helps, in these ways. So it provides electrical isolation to prevent corrosion. Okay, how electrical isolation comes into picture, I will explain. Uh, the buried pipeline is normally provided with a impressed current cathodic protection. Basically, to avoid the galvanic corrosion happening in the pipeline because of the soil properties, corrosive or the electric potential carrying properties in the soil. Wet soil and dry soil can create some kind of a medium across which some kind of a galvanic cell can form, and on the same pipeline pipe, anode and cathode pair can form, and it can exchange the ions, and then one point will lose the metal, other point will get the metal. But this is not advisable, because where the point which is going to lose the metal, losing the ions, is basically nothing but like some kind of a metal loss, and it is reduction of thickness, and it cannot withstand the design pressure eventually, so the thickness will go below the required hoop thickness, what we have seen in the past. So the pipeline is impressed always with the electric current, which is called CP system. This current, you can understand that the above ground pipeline is connected with the station pipework, which I have explained to you, that the main facility, the pipeline is transporting the fluid from one facility to other. So the main facility is having all these pipe racks and structures and a lot of equipment which are grounded, and earthing is provided to all of them. So the impressed current that we are trying to keep the pipeline passive from the galvanic corrosion, that current may leak through to this earthing system of the facility provided, to which the pipeline is connected. And if that happens, then the pipeline's CP protection may become very weak, and eventually a galvanic series can form, and then it can start corroding. So to avoid such leakage of cathodic protection impressed current to the adjacent structures in the station, isolation joint is provided at the transition point where the pipeline goes from above ground to buried. Isolation joint is having internal features in such a way that it will withstand the pressure and flow in the pipeline, but the non-conductive material is provided with the seals and high pressure seals in such a way that it will not allow it will basically break the conductivity of the continuity of the conductivity. So current cannot be conducted across it. It will get barrier, because of the non-conductive material. When we see the details of the details of the isolation joint later, when we design the individual element, we'll see these features. But basically, it is breaking the conductance of the CP current leakage to the facility. And it also sometimes provides the surge protection for the pipeline system. If there is a surge happening, then it will not allow the surge circuit to be completed across it. So that helps. So we'll study the impressed current CP system also, and the IJ isolation joint cross section, and the other alternate means for providing that in detail later. So let's see the pipeline corrosion monitoring fittings. Basically, along the pipeline, okay, when the pipeline is buried and going along very, very long distance, okay, even though we saw that the pigging is done regularly to control the corrosion from happening, it will remove the deposition, it will try to scrap the deposition, it will try to move the stagnant liquid or water from the low points away. Still, there is still a possibility of some corrosion reaction happening in the pipe, because pigging also has a limitation. It cannot be done every day, okay, or every hour. It can be done maybe once a week, or once a month, or once in quarterly once, or 6 monthly, depending upon the cost involved and the limitations or the impracticalities involved in that. So the pipeline, if the corrosion is taking place, okay, if corrosion reaction starts, then it is always worth measuring that, to predict that what kind of a corrosion can happen, because the corrosivity of the service fluid, because you are doing the analysis, and you can predict that, okay, this service fluid is having corrosive properties against the pipeline selected pipeline materials, say carbon steel, then you should also be able to ideally predict that if the corrosion is happening, then how much it is happening. So for that, the corrosion monitoring pits are installed along the pipeline. Normally, they are provided at the start and end of the pipeline, and also at some strategic locations at the low points along the pipeline, where the stagnant liquid possibilities are there, and it can create or it can kind of aggravate the corrosion at such points. So in the pit, what is done is corrosion coupon and corrosion probe. These are two types of monitoring fittings installed from the bottom of the pipeline. They are basically welded to the pipeline, and they have the hole punctured in the pipeline, and the probe is installed. I will show you also how they look like. So there are two small tiny rods or tiny features shown below in the sketch. First one is having a disc at the top, which is called coupon, and the second one is having two strips connected at some distance at the top. They are called probes. So corrosion coupon and corrosion probe are inserted inside the pipeline, not in the flow path, but at the edge of the ID of the pipeline at 6 o'clock position at the bottom of the pipe. Why they are not inserted inside the flow path? Because when the pig is going to pass, it should not get stuck at such points. So these probes or coupon are exactly kept flush with the pipe ID. Okay, it will not protrude inside the flow path of the pipe where the pig is going to pass. So this coupon, let us see corrosion coupon first. So corrosion coupon provides a representative sample of corrosion taking place in the pipeline. So what happens is this coupon, there are some special tools which can be connected at the bottom of this assembly, and through which the online while the flow is taking place, these special tools can withstand the pipeline pressure. So through this, we can remove the coupon out online, temporarily, and check the coupon, the condition of the coupon, which gives us representation of what must be happening in the pipeline. And normally the coupon is made of the same pipeline material. So if the coupon is seen as losing the material, there is corrosion happening, is observed on the coupon, then it is anticipated that the similar kind of a corrosion reaction must be happening in the pipe. So this is called corrosion coupon, which is basically direct representation, but it has to be removed and checked at periodic intervals. Whereas probes are basically two strips connected at certain distance, and the voltage across these two strips is recorded by connecting the wires to the analyzing system, correlation system. So if the corrosion is happening on these strips, metal is losing, that means the distance between these two strips is going to increase, and that change of distance will result in different differential voltage across them. And by measuring them continuously, and since they are like connected with the wires, they can also be connected to the control room, and you can continuously measure what is happening, the difference between these. And then if the based on that, it can be correlated, and then some kind of a algorithm can be developed to decide the anticipated corrosion rate in the pipeline. So corrosion, as this is online, continuous kind of a measurements can be taken. It does not need the retrieval, the online removing it out and then checking. Though it can be done, but it is only done for the some kind of a repairs required. But coupon needs regularly removing them out and then checking the condition of the coupon, whereas probes provide you continuous online measurement. So these two are the techniques typically used for the corrosion monitoring of the pipeline, just to get the representative feel of what kind of a corrosion rate must be happening in the pipeline, and accordingly the mitigation measures then can be set. Like the peeing frequency can be decided, corrosion inhibition, injection rate can be decided, and things like that. And many times the fluid properties in the pipeline, because if it is not from the treatment facility to treatment facility or export, but if it is a gathering system, then the fluid properties coming from the reservoir may vary, across the over the period of time. And if that happens, then the scooper and probe becomes very important, because they can give you the representation that initially the corrosion rate was lower, now it has increased. So according to the variation in corrosion rate, the mitigation measures can be altered or can be added. So it becomes, these are very important part of the pipeline system. So we have seen, we'll just recap now. We have come to the end of 103 part 2. We'll just recap quickly what we have done in this. We have seen a typical pipeline system and its elements. Okay. Uh, Hope the beginners in the pipeline field, design field, can now have a better imagination and understanding of what is a pipeline system and what are the key elements of a pipeline system. Design of each element is one of the main tasks of the pipeline design engineer, which we will cover in the future series of the lectures. Uh, we will cover the guidance of design and the procurement aspects also for the individual elements, so that not just how the element looks like and how it is designed, but also how to specify it and how to procure it also we will try to cover, so that these series should become like kind of a easy guidance for everyone who is going to design those elements and design the pipeline in future. That is the idea of doing this series of lectures. Hope you are finding these lectures interesting and useful, and we will unfold all these elements and design, as well as the calculation part for and the stress analysis part when we go further in this series. Your feedback and comments are most welcome, because then accordingly I can do some changes, and then I can add some more valuable information based on that. Okay. Uh, Thank you very much, and that's it from my side at the moment. See you again with the future lectures of this series. Thank you very much. Bye bye.